Welcome everyone. In this video, we're going to talk about how to reparametrize a curve with respect to its arc length. So here's an example for you. Let's reparametrize this curve right here. This is a vector valued function, and let's call this our curve C. So first thing you want to do is find its arc length starting from t equals 0 in the direction of increasing t value. So there is no ending. We're just going to integrate in the following way. So let s of t be our arc length. We're going to integrate from 0 to t without any ending for now. And in the integrand, we're going to have, this is going to be the magnitude of r prime of tau d tau. So we just introduce another variable in the integrand. So let's go ahead and do that. So first of all, we're going to find r prime of t. First, we need the formula for r prime of t. So let's differentiate r prime of t. So we differentiate component-wise. We're going to take the derivative of 2t respect to t. That will be 2. Derivative of this piece, that's going to be -3. And then the derivative of 5 plus 4t, that's going to be 4. We're differentiating respect to t. And then second, we're going to compute its magnitude. So that's going to be the square root of each component square when we add them up. So 2 squared, that's going to be 4. -3 squared, that's going to be 9. Plus 4 squared, that's 16. So we add them up, we're going to get the square root of a 9 and 4, that's going to be 13. Plus a 16, that's going to be 29. All right, so now we're going to substitute this in here. And we can just call that r prime of tau instead of t, because t is our upper limit of integration. So in reality, we're simply integrating the integral from 0 to t of r prime of tau. So this would be the magnitude, which is square root of 29. So this is square root of 29 d tau. And this would give us the following now. So this is just integrating constant respect to tau. So we have square root of 29 tau evaluated from 0 to little t, which means now we plug in the upper limit and lower limit of integration, and we have our s of t is going to be the square root of 29 little t. All right, so that is our arc length function. Now we want to reparametrize this. What that means is you want to solve for t in terms of s. So you can simplify things and just rewrite it this way. You can say s is equal to square root of 29t. And then by solving for t, you get a function of s, which is arc length. So t is just simply going to be s over the square root of 29. There you have it. And this is what we're going to plug in right here for each t, and that will be a reparametrization of the curve C with respect to its arc length. So how's that going to look like? So our reparametrization would be the following. So our reparametrization of our curve C with respect to, let's just abbreviate that with respect to its arc length. It's going to be, so we're going to plug in s over square root of 29 in place of t. So our r of s of t of s. So t of s, this is going to be, so the first component is 2 times t. 2 is s over square root of 29. So that's 2 times s over square root of 29. So sorry for the spacing limit. I'm just going to rewrite it. So this is 2 times s over square root of 29. The second component we have is 1 minus 3t. So that would be 1 minus 3 square s times s over square root of 29. And then the last component is right here, 5 plus 4t. So that's going to give us 5 plus 4t is going to be s over square root of 29. So there you have it. Your curve has been reparametrized with respect to its arc length. All right, I hope this makes sense.